So I come again that in this section, we are going to investigate the relationship between the certain kinds of line integrals on closed paths and double integrals. We have already covered double integrals in the previous topic. So it will be it will be just building on what we already know, whereby we said when you're doing double integral or triple integrals, that was under topic 2, that is the multiple integrals. We said when you're doing the double integrals or the triple integrals, when you're maybe you have two variables, that is x and y. So when you're integrating with respect to x, every value that is of y, you treat it as a constant, and vice versa. That is when you're integrating with respect to y, every value that has x, you treat it as a constant. So going by the explanation here is that let's start off with a simple curve, closed curve. You can see here a simple closed curve. The curve is the line, and the region will be called D. So D to be the region that is enclosed by the curve C. Here is the sketch of this curve. And notice that because the curve is simple and closed, there are no holes in this region D. And also notice that a direction has been put in on the curve, as we already said. In Green's theorem, you're going also to deal with another theorem called the Stokes theorem. So in Green's theorem, we usually deal with the directions are usually counterclockwise. That is the anti-clockwise. So you can see those directions there. We will use the convention here that the curve C has a positive orientation. So if it is traced in a that is, it is traced out in a counterclockwise direction, that is anti-clockwise. And another way to think of a positive orientation that will cover much more general curves, and you will see this later on. So this is what the Green's theorem states. So we are going, most of the time we'll be given some values, and we are going to be, we'll be told to verify them using the Green's theorem. So I want you to copy that explanation, this explanation here, that let's see be a positively oriented, piecewise smooth, simple closed curve, and D to be the region that is enclosed by that curve. And if P and Q have continuous first order partial derivatives on D being now the enclosed region by the region by the curve C, then you can see this is what the Green's theorem states. So copy this in your notebook, then we can put this into context by working out a relevant example. So I believe you have copied that. You'll notice some new formulas here, or some new denotations. We're going to know what they are called. When working with a line integral in which the path satisfies the condition of the Green's theorem, we often denote the line integral as this. You can see there is the integral sign, and then there is a zero between the integral sign and a C. To see it mean that it indicates a curve that is a contour and it is enclosed, and its integration is performed counterclockwise. You can note it using this type of denotation, this one here, or this one. You note for this one, the other case, it has a direction that is counterclockwise. So just the use of that zero, it just means that it's a closed curve, and also sometimes when you use the curve that the zero that has that sign, that is the sign of direction, it means that the orientation that you're going to deal with here is counterclockwise. So before these denotations, do assume that C satisfies the conditions of the Green's theorem. So we are going to see what those conditions of the Green theorem are. Actually, the conditions are just here. So you can see, like here, these are partial derivatives. Yeah, you have covered this already. Partial derivative. You can see, like trying to read this mathematically, is that the integral, the closed integral of p with respect to x and plus q with respect to y is equals to the double integral of region D, and then the partial derivatives of q with respect to x minus the partial derivative of p with respect to y dA. So you can look at this example one. I want to believe that you're good students. You already have attempted them because they were there. Um, so you're told use the Green's theorem, example one. Use the Green's theorem to evaluate the value of that closed curve, and you're told it is xy dx plus x squared y cubed dy, and you're told the closed region C, it is a triangle and it has those vertices. So this is the solution. Before, maybe you should not be seeing it. So we are told the C is the closed curve, and it is a triangle with the vertices 0, 0, 1, 0, and 1, 2. So when you try to solve such an example, they're told to verify the Green's theorem of that enclosed region. So you can see it's necessary for you to draw that region because you have been given the coordinates. The 0, 0, that is the origin, then 1, 0, 1, 2, and you can see it will come out to be a triangle. It has already been told here that it will be a triangle. So once you draw that, this is what happens, and you can see the directions. So once you draw that, the necessity why you're drawing this is to find the limits, because we say this we are going to use double integration, and you know for double integration we usually have limits, and you can see for our case here it has two derivatives, that is x and y. So therefore you will need to see the limits of x, and from our example here we can deduce that the enclosed region, its limits for x are from the lower limit is 0. You can see it is from the origin. So is the case for the upper limit, and the upper limit for the x variable is 1. You can see here. You can also read this one directly from the coordinates here, because you know the coordinates, they read x, y. So just need to check the lowest value of the x coordinate. You can see definitely it's a 0, and the highest it's 1, because you have 1, 0, 1, 0, the 0.10 you can see there, and the other one is 1, 2, 1, 2 here. So the limit for the x variable, it is the lower limit is 0, the upper limit is 1. The same case for the y derivative, or the y axis from the axis here. The lower limit, you can see it's 0, obviously, and the upper limit, you can see the value here is 2x. So the limits for the y-axis or the y derivative will be from the lower limit being 0 and the upper limit being 2x. So we already have now uh, the inequalities that define that the enclosed region. So once we have that, we can go right ahead and identify the line integral P and Q. P and Q from our definition here. We said if P and Q are continuous first order derivatives of D, we said D is the enclosed region. So we want to identify these continuous line integrals, the P and the Q. How are we going to identify them? We are going to identify them by looking at our equation here, and they are already given. You can see for the P it will be xy because it will be with respect to dx, and for Q it will be x squared y cubed. So you can already read them directly from the question. So we have identified our P and Q integral lines. So P is equals to xy and Q is equals to x squared y cubed. So once we have that, the first thing, those are the major things that you need before you proceed to do the to verify the Green's theorem. Because you need first to have the limits, which you have already seen the two limits for the x 0 to 1 and for y 0 to 2x, and then we get the line integrals, the P and the Q. For P, it is here, that is the x, y, and for Q, it is x squared, y cubed. So once we have that, we are going to use this explanation, that is the Green's theorem explanation. You don't necessarily have to cram this, maybe I can add that. You just need to, it is there, this Green's theorem, it is there in the mathematical table. So you just need to, but with the time you come to realize that this thing they usually stick in your head the more you practice them. So we have the limits, we have the line integrals. So what remains? We just need to verify the Green's theorem. To verify the Green's theorem, we said these line integrals P and Q, they must be equal to that the enclosed region, and it's the first order partial derivatives on the enclosed region D. So our enclosed region is this one. This one is the one that we can call D. So we are going to try and verify this and see what is its partial derivative with respect to the enclosed region. So the first thing that you do, you put the left hand side, and you try to verify the same on the right hand side. So using the closed integral formula, you put it here, and then use the double integral sign, and then you differentiate the normal way, differentiating with respect to y with respect to x, dy dx. So as you copy, note that this is the partial derivatives. I had shared with you on the portal something to do with partial derivatives. I hope you actually did look at them. Yeah, the partial derivatives. I had shared with you some examples there. So from here, this is the rest is just basic mathematics, yeah. Because from here you just do the partial derivatives of the inequalities that are given here, and you can see our limits, uh, 0 to 1. That is for it was for x, and then for y 0 to 2x, and then this is our inequality, and then now we integrate them the normal way we have been doing on multiple integrals. So you can copy that solution, then we look at another example. In case of any question, as you copy, I can assist you. Let me know if you need any assistance. So I hope you have copied. We can look at another example. Let us look at another example. I want you to attempt this example. And unfortunately, we are running out of time. What will happen once the class, because it is limited to 40 minutes, once it will automatically switch itself off. So after it switches itself off, I would like you to log in again using the same credentials. So even as we do that, try and attempt this example. Copy this example and then attempt it. I don't know if it's legible. So attempt this example. So we're going to verify that those inequalities, f1 is equals to y squared minus 7y, and f2 is equals to 2xy plus 2x, and for the circle, x squared plus y squared equals to 1. Try and attempt that, then we look at its solution.